Okay, so hello everyone and welcome back to the AI class. Last time we were going through learning for AI systems, and for learning we have seen so far there is a set of methods. One of them is the discriminative methods that we are going to start today. First, we started with generative methods, and for generative methods we seen models designed for clustering purpose, and the JMM last time, the Gaussian mixture, and also we've seen the K-means algorithm. Now, these are examples, and once you are going to have machine learning class, maybe you can see more examples. During your project as well, you are going to see more examples. So I keep the space for you to explore more examples. For this particular set of methods, which is the discriminative methods, we are planning to see first K-means, KNN, and then we are going to see the SVM, support vector machine, and the K nearest neighbors. Okay, so but before seeing that, so this set of methods is classification method. So some methods could be there for regression or classification, but it is not for clustering. Okay, it's not for creating groups of similar things. In that case, means previously we were working with unsupervised data. Okay, and in order to create groups or clusters, we were based on similarity metrics and distances. Now it's completely different task because we are in the context of classification. So it's extremely important not to distinguish between both clustering and classification because both of them are extremely different tasks. So for classification, we'll see basic concepts and how it works. Then we are going to go through. Before moving to the different methods, we are going to go and explain the different evaluation metrics, because if what we are going to see is examples of classification methods, but if you have a classifier, so you have performance. We were talking briefly about how to evaluate error, how to evaluate performance, but now we are going to dive with more details here, especially that you are going to use this for your final project. So it's important to know what exact metrics you can opt for or choose. So to start with, just to refresh your memory, we have so far seen two types of learning, the supervised and supervised learning. When you decide to work with supervised learning or unsupervised learning, it depends, first thing, from the task you are going to perform, and second thing, from the available data you have. Sometimes the task is classification or prediction of a given class. It's done due or after a whole training process. So if you have training, means you need supervised data. Otherwise, if you are in the opposite case or scenario, you have unlabeled data, there is no training process. What you are doing is just to explore or discover alternate patterns or structures given your unlabeled data. Okay, so now what is classification? We're talking about classification. We are mentioning the context, which is the context of supervised learning, which means supervised data. What we have? Labels, which means for each sample, which is described by a set of attributes, like for a person, I can describe this person with its name, address, ID, height, weight. These are attributes. Now, it depends on what task I'm going to perform. I may have a set of tests of labels or classes to which belongs this sample, like for example, male or female. This is the most simple one. So now what we will have is this task of classification. In the case of machine learning, like context, it's just about predicting the value of the label. If I have, for example, a woman as a class, I am going to have a set of features. I'm going to predict the class, given that this class is hidden. So it's the same like before, what we did before when we were talking about clustering. When we talk about clustering, we say that supposing this classroom we have in this table, like for example, male are sitting. In this table, they are female sitting. Someone new is coming, and we are going to assign it to one of the groups. When I say assign one to one of the groups, the someone coming is keeping his ID home, keeping the level or class home. So it's unsupervised data. How we were deciding about assigning him or letting him sit with this or that table, it's based on metrics. Like, for example, I'm checking the hairstyle, I'm checking the clothing, I'm checking like things, okay, that would let me, for example, like say this is a male or female, just as simple as this. Now it's a different task. We have someone who is sitting in the like door. This person, mainly anyone is coming is saying, just show me your ID. In the ID, the most important information, it's male or female, which is the class of that person. That much people, this like bodyguard or person sitting on the door is seeing, he's trained, and we call this training data. So he's seeing that much people, so that someone is coming. Now he's saying, I forgot my ID. Okay, well, I will let you come. But what he will do, he's going to predict his class, okay, based on the previous examples that he's seen, and then he's going to say, okay, you can sit here or there, okay? So this is classification task. Here we identify or assign for a given observation or data point the corresponding class or label. This is what we were discussing. So consider it as an instance of supervised learning, known as clustering in unsupervised learning. And here classification quality evaluation, which means at some point, someone can get confused and we are not sure if this person is letting sit, for example, with this or that like group, is it the accurate or it's not accurate solution that he's providing. So this is where the quality evaluation comes. And now what is our goal? It's that given data, what is our data in this case? The data is described, as I was mentioning, with the data records. And this data records is given key attributes, first, second, third attribute, and so on. And for which each one there is a class. And the class is here the label. Now the goal is to learn a classification model like this, like bodyguard, for example, I was given as an example. And this is the model. And this model is going to learn to classify new data from the data that can be used to predict the class for new or future cases or instances. So what I may introduce at this level is the test. So if it is trained, so this is training data. If someone like or a new sample or instance is coming and he didn't see that before, it does not belong to the training data. So this is a test. It's test or future example. Okay, now let's take some example to just illustrate the idea of classes, because I'm sure that few students here are taking ML class. So when we talk about class, it's like the label exactly. And if I have an email, the class could be, this is spam or not spam. And in this case, the data set is
email. Spam.
No, what type of
Label.
Yeah, it's supervised,
Binary.
it's labeled, it's binary. You're doing good. So binary, because this is binary classification, whether it is spam or not. So we have only two classes, okay? Otherwise, if we have more than two classes, like here also we have two classes. If I have a product, the product could be good and having a positive review. Otherwise, it's negative. So this is also an example of binary classification. Otherwise, if I have more than two possible classes, like for example, for a business article, I may guess it belongs to the class accounting, finance, economics, or marketing. So this is the case of multi-class classification. Great. So what we need now to know is if we are working on classification, there are two steps. The first step is to construct a model from the learning data. From the training data, I need to build or construct a model. The second thing, now I am going to use this model for two main purposes. The first one, I have a model, but it's not every model is performant or accurate. So I need first thing to measure or test the accuracy of the model, given the test data set, which is a set that has not been seen before during the training. It's a different set from the training set. And I can also use it in predicting new features or new observations, okay? So we start with the first step, which is to build the classification model. And for this step, what we have the whole data set, the lablet data set. What we are going to do is to divide our data into two classes. So the first class, the first set is the training data, and the second set is the test data. So the training data is going to to be there when we are talking about the learning phase or the learning process of the model. And next, when we want to evaluate our model, it's here where we talk about the testing data. So in general, what we have, the model must be trained well, which means when we say our model is trained, when, for example, it's converging towards some settings, if there is a new sample, it could give you the accurate results. So in this case, in general, the training data set is having more data than the testing data set, and it's 80%, always we do 80% for training set, it could be 75% or around that. And for the testing data, it's the remaining, so it's 20% or 25%. So now, I may ask you, so if you have the whole data set, okay, which is supervised data, how can you split this data into training data and test data?
We shuffle it and then split.
Great. So Farah is saying that we shuffle it and then split. So is everyone familiar with the word shuffling or the concept of shuffling data?
No.
I mean, I hope so. I think it's like shuffling cards, right? Just sort of mix it all up, or is that different?
Okay, so let's suppose we have examples of data. Okay, sorry. I will give it the board and explain things. So imagine that the recording of data that I have is saved in a CSV file, okay? So this CSV file is having, let's say we are in the context of binary classification, two classes. So I have, let's say, 10 let's say these 10 samples, where for what I have is always the class, okay? So here I have my class, and here you are going to have the features for each of these classes. So we take the simple example, male or female, okay? So I am having the male data first, okay? Let's say my data is balanced, so I have, let's say, 5, 5. So I have 5 first samples for male, or 6, okay, 5. And then I have female. Okay, you can imagine a scenario where your data is given in this order, okay? And I am just saying that you need to split your data into training and test. What you will do, you will say, I will take the first 80% or 70% of the data for training, and the rest, how much in this case? So it's 20% for testing, okay? What is happening in this case? You are having your model trained on male, 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 and just one female. So if you are coming in the test data, you are giving only testing on female instances. So even he don't know the features or attributes for female. So what we mean by shuffling is like mixing, okay? Like, for example, I am not going to keep my data in the order. I am going to keep one sample male, female, then maybe male, male, then female, female. The rest is male is coming down. So that within the first 80%, my model is seeing both classes. In this case, it's just 2, but sometimes imagine having 7 or 10 classes. So if your model is seeing this example during the train, So it's very normal if you're giving him a female, he's in a female, he can guess. And also you can test with a male and he knows the features and examples from male, so he can also guess. So sometimes when you are working whether with machine learning or deep learning in AI with learning, one of the biggest problems is with data. Sometimes you think that everything is okay, import, I don't know what, read, and you are done, you are checking, balanced data, everything is cool. At the end, your model is giving very bad results. Sometimes it's overfitting. It's like giving bad accuracy. You ask yourself why, and this was even happening with me many times. So I just forget to shuffle data, which is the very important step, which means that I forgot to teach my model or let him learn very important features, okay? So you must be very, very careful with this point. First step is to shuffle your data. It means you mix your instances, you don't keep it in the order, so that during the learning process, the model is seeing enough examples or samples or classes, let me say, so that when you are testing your model, you are able to like really test. It's not like I don't teach you something, it's exactly this. I don't teach you something, and in the exam I'm asking about that thing. So you need to teach your model first, show him everything, every single class, and then you can ask your model during the testing phase. So this is about shuffling. The second point, let's suppose now my data is shuffled like that. How can I split it?
8%.
How can I do that?
8 times the land, for example, or there is a lot of.
No, how I have there one folder, okay? It's like one file. It's like data set, it's called all data set. How can I from that generate two sub data sets? The first data set, it's called training data. The second one is test data.
There is some functions to do that, but we can do it manually.
You can do it manually. This is the very simple thing.
Like,
You select like 8 first samples, okay? Control X, new file, train data. The last 3, Control X, test data. We are done. But this is only when I have 8 or 3 samples. Imagine having billions. So in this case, Python is making it simple. So with sklearn, like library, we can use the function train test split, and this function, which is already there in Python, can you give it like the result for this function is going to give you from the whole data set, which is X, and its labels, which are Y, means the supervised data. You are going to specify the test size, which means 0.2 here, means 20% of the data is going for the test data, okay? Then the remaining data automatically is going to be for what? For the training. And what is going to be the output of this function? It's going to give you for the train, the X and Y, means the data and its labels, and also for the test, the X and Y. So this is one example. There is another example, which is cross-validation. Cross-validation is a technique which is extremely useful, and it has really good impact when we talk about like improving model accuracy and so on, especially in the context of reduced size data sets, means small data sets. Okay, so if I have a small data set here, the idea of cross-validation is to train and then validate the model on several possible sections of the train set, which means that given, imagine this is my train set, okay? You see? So I'm going to, it's called k-fold, which means I am going to divide my initial data to k-folds. When I say fold, it's like a subset, okay? So here we are dividing it to 5 folds, okay? What will happen? I have 5 folds from my data, and each time I am going to consider 1 fold for the test, and I'm going to train my model on the remaining data. Then I'm going to switch. Another like different fold is going to be for the test and remaining data for training. Each time I'm going to consider a different fold for testing and the remaining data, which is automatically different for training. And in this case, what I'm doing, I am letting my model like face different data and test it on multiple data, which is going to give me multiple results if we are going to consider the performance. So in this case, for split 1, there will be a given performance. For split 2, there will be a different given performance until the number of folds or splits. So in this case, how to compute the performance metric for the overall like cross-validation technique? It's to average all of them, okay? So here, the performance metric from each fold are averaged to give the final assessment. Is that clear? Now, how to create this token if we are trying to code? So we are going to see, like, after some time, the k-neighbor classifier, keep it apart. Now what we are going to discuss is the cross-validation. So in this case, we are going to use a library which is called cross-val score, as mentioned here. You are going to import this one from sklearn model selection, okay? And what you will do, you are going to give as parameters your classifier, because you need a model at the end. And this model you are going to apply to feed data. And this data is not going to be fed simple like train and test. It's going to be k-folds, okay? It's cross-validation. So you use cross-val score. And in this case, we define the train and labels. And we have here, this is equal to 5. It's what?
Okay.
Okay, this is the number of folds, okay? And by default, it's equal to 5, okay? Otherwise, you can set it, for example, 10 folds, 11 folds. It depends on the size of your data. As I was teaching you last time, always, if you have any function, for example, you don't know what means scoring here, you need to check the official documentation, okay? Or ask ChatGPT. And after this, some like what we say, parameters are coming in the order. You do not need to mention their initial name, okay? Otherwise, here CV, it must be not the third one or the fourth one. So this is why we mention CV equal. This scoring also parameter could be at the end, like 20th or at the end of the list of parameters. So this is why we specify the name equal to what value could be given to this particular parameter. Is that clear? Okay, so just like this, we can perform cross-validation. This is an example that we were just discussing. If I have 5 folds, how it works, how I am going to compute the final performance and so on. Now let's move to the main part of the first step. We are still talking on building the classification model. So now I have my model, which is a machine learning algorithm, okay? And what is going to be, what I'm going to feed to my machine learning algorithm? We just said that the machine learning algorithm is going to be trained on training data, and it's going to learn from this training data. If it's going to learn for which purpose, so it is going to give a predictive model. It's going to predict whether like a class for a given example from the test data, which means I have my trained model now. It's ready to predict new like for new data. It's going to predict the class, for example. So the input for the predictive model is going to be your test data, okay? Otherwise, it's not only when we talk about classification that we predict the class. We can sometimes predict the accurate value, okay, of that thing, probability value or something. So now, if we have now our predictive model, the second step is to evaluate the classification model, which means if I have or I'm building, given a training data, some predictive model, it must not be the final one from the first step. It takes long time. It takes a whole process to finalize or converge towards the final predictive model. This happens how? It happens like each time based on the obtained test results that you have from your predictive models, you can like make modification to your algorithm, ML algorithm, and again, obtain a new model and keep doing this. Like, let's suppose in the start what we did, I have training data, test data. Maybe I found some overfitting here. I thought like from shuffling, sometimes this here is related to data. Sometimes it's related to the model. We will see like the KNN, for example, it's going to be the K nearest neighbors. So it's a very simple concept of this algorithm. Nearest neighbors means that we are going to measure the distance and we are going to see the most near to that point, which means, and K is always an hyperparameter. So K could be 1, could be 2, could be 3, which is part of my model here. It's not related to data, it's related to the model. So sometimes I try with K1, I see it's not a good result. I try with the K2, I see it's not a good result. So we'll see so far, this is called something when we're making modifications within the algorithm itself, it's fine-tuning, hyperparameter fine-tuning, okay? So this is for the second step. Next, what we have, when you are satisfied with your results, you use the predictive model to label new and classified data, which is the main purpose from training. Okay, I'm showing like my model, many cats and dogs. What is the main purpose? If I am having like some camera, I'm checking if there is a thief or just a cat, it's going to classify, it will guess. If it's a cat, then everything is okay. So this is where we are like from data into insights and insights into decisions, okay? So this is very important step. Next, here I wanted to discuss points related to the evaluation of the performance of the classification model, which is essential for main points that are to know if the model is significant globally, which means I ask myself, my model, does it really reflect causality? And this is the main purpose from introducing evaluation performances or measures. The second point is to get an idea of deployment performance, because if you will deploy some model, it's not a model with 20% accuracy and we are planning to deploy this model, okay? So I ask myself, what will be the reliability or the associated cost when I use this model? It's deployed. So to compare several candidate models as well. If I have a set of models like you are going to have for those choosing the ML project, you are going to compare between a set of ML projects. So which among several models will be the most efficient given my objectives? So for the ML project, you are having a data set, and each time you are going to see which is the most performant. For this, you will need the evaluation measurements or performances. We will see this. So what you do is that you have your training data. The first step is to train. Now your algorithm is learning. The output of this is going to be a model. You are going to test this model given a testing data, and at the end you're checking the accuracy. The accuracy is the very basic metric. We will see so far other metrics. So the measurements and evaluation of the performance of a classification model is always done on the test sample. We cannot measure given the training data. However, at some points we can talk about training accuracy and validation accuracy, or the loss for training and loss of accuracy. But the final accuracy of your model, it's given the test data. You cannot come and say, I am having 100%. And by the way, this is happening I have seen papers published in good venues, and they mention a table, for example, showing their results, accuracy. When I go and check, they are just mentioning the training accuracy, which is completely unacceptable. Okay, so you need really to be careful. You cannot say it's training, every model is going to be trained until converging to 100% training. But when your model is learning 100%, are you bringing new data? Is it 30% like accuracy or 100? If it's 100, here I will accept your paper. If it's 30%, excuse me, what are you doing? There is an overfitting. Okay, so it is necessary to test the performance of the model on data which have not been used to build the classification model. And in this case, now we are going to start with the evaluation metrics. We were talking about accuracy. The accuracy could be seen even in the confusion matrix. We've seen an example of the confusion matrix before. I remember this. So the idea is to have a matrix. In this case, it's the dimensions here are the dimensions of this matrix are 2 by 2, which means how many classes do you have? 2, which is a case of binary classification. So it's positive, yes, for example, positive, here, positive, negative, negative, positive, and negative, negative. So here, this is the key for every interview. If you are planning to have job or internship in ML, they ask you about confusion metrics, F1 score, accuracy, precision, and like these metrics. It's a must. So you need just now to be awake, okay, and concentrate, because once you learn this, it will be there forever. So positive means correctly classified. Negative, let's say they are not correctly classified. If I have a confusion matrix, here I have the actual values, which are positive or negative. And the predictive values could be correct and could be like wrong, which means the predictive value for a positive could be positive and that's true. This is why we talk about true positive. The predictive value could be false at the time that is like positive at the time the accurate actual value is negative, which the case of false positive, or the opposite. It could be negative when it's positive. We talk about false negative, and negative when it's negative, which is a true negative, which is negative, and it's correct that it is negative. So keep in mind this, like true positive, false negative, and true negative. So this is the key for computing the accuracy rate, the recall, the precision, and the F1 score. Okay? Is that clear? So if I am going to give you now the formula for computing accuracy, and I start saying true positive, false positive, true negative, don't get confused. Always keep this picture in mind. Okay? For example, true negative is negative, which is truly predicted as negative. True positive is a positive, which is correctly predicted like true positive, and so on. So let's start. Okay, I just want to go to the example. Okay, for the formula. Now, if I talk about the accuracy, which means it's a metric to evaluate, given like a classifier, how accurate is it? How accurate is it? I am going to check the number of correct predictions, because if it's accurate, what I care about is the correct among or as compared to all, correct and not correct. So the formula for accuracy is the true things, which are true positive plus true negative, divided by the whole thing. We have 4 possibilities: true positive plus true negative plus false positive plus false negatives. Okay? So the accuracy may be misleading when there is a great deal of inequality between the number of positive and negative labels. So we are aware if there is any metrics, we cannot trust that 100%, but like we find the community, they are using this metric, so we keep using it. One of my research works, or my PhD, I was working mainly about explainability and robustness. So we introduce a new metric, which is the robustness. It's there in the state of the art. You can take a look. So robustness is a metric which comes after accuracy. So we suppose the accurate result and check the robustness. So given adversarial examples, for example, is your model still predicting correctly or not? Still having like robust results or not. So always, if there is a metric, it's just like a metric. You don't think that, okay, a model given 100% accuracy is the best model. No, a model given 100% accuracy must also be given 100% robustness to be able to deploy it, for example, in safety critical domains. Okay, so next now, the precision. The precision is when we consider the case of positive and we care about the true positives. Okay, so it is the we divide the true positive, the number for sure of true positive, by the sum of true positive and false positives together. So precision is another measure for evaluating classification models, and it is the proportion of positive indications that was actually correct, because here true positive and false positive. When there are no false positive, the precision is equal to 1. Okay, it's not like the in accuracy, when your model is accurate, it's given 100%. Okay, and the precision answers the following question: what proportion of positive identifications was actually correct? And in this case, a classification model producing no false positive at a precision of 1. Okay, so we have the last or before last one, it's the recall. Recall here considers the number of correctly classified positive examples. So this is why here you have the true positive divided by the total number of actual positive examples in the test, which is the sum of true positive and false negatives. Okay, false negatives are actual positive as well. Okay, so the recall allows you to answer the following question: what proportion of true positives was identified correctly? In this case, it gives an indication of the proportion of false negatives, and a model producing no false negatives has a recall of 1. Okay, 1 or 100% is the same. It's like for probability value, it's the maximum is 1, but we can translate it into percentages. So examples, we keep it for the review. Now what we have, I wanted to start with this quickly. Yeah, the F1 score is the last metric, and it is hard to compare two classifiers using two measures. So F1 score here combines both precision and recall. So this is why you find in the formula, you use the precision twice, means multiplied by 2, and divide with the sum of both precision and recall. And F1 score is the harmonic mean of precision and recall. So we can find it like this. So in this case, the harmonic mean of two numbers tends to be closer to the smaller of the two. So for F1 value to be larger, both these P and R must be larger. So this is going to increase the whole value for the F1. What we have here also, we can consider the ROC curve. So the ROC curve is what we have in this case, the evaluation of true positive rates and false positive rates. If I consider the true positive, so I have my true positive and I consider true positive plus false negative. If I consider the false positive, so I have false positive divided by true negative plus false positive. Okay, and this plot or this curve is, I will show you examples after this, but also we can consider the true negative rate, which is true negative is the same as this, but we are considering the rate. Okay, so and if we want to consider the false positive rate, it's the complementary to the specificity, and the specificity is this TNR, true negative rate. Okay, so it's just metrics. Sometimes we can combine two metrics to come up with a new metric, because if we are combining, it's reflecting more. If it's I don't know, to explain, for example, I have the sensitivity. The sensitivity is the same like true positive rate. Here, the specificity, it's the same as true negative rate. at some point, I can like deduct or conclude specificity given sensitivity, or it's the opposite, okay? So the ROC curve now is the example where I'm going to go straight to the curve. So the ROC curve is if we have the false negative rate here by the true positive rate here, and we have these plots. So what we have, for example, C1 and C2, and we have this line in the middle. If you can see here, it's dividing your whole space into two equal parts. It's like the diagonal for this like rectangle, okay? So what you can see that here, both ROC curves C1 and C2 are above this line, which says something, we will see, okay? So here we have two classifiers can have two metrics, which are called ROC curves. How to evaluate now? How to draw? So it's like you have your false negative, true negative, false positive, true positive, and you keep each time presenting the dots or the like elements of your curve given the numbers like a false positive rate by like a true positive rate. And finally, we talk about the area under curve when we say like, or which area it's like under the curve. So what we see here, which classifier is better? Is it C1 or C2? How to decide this? Here, it depends on which region you talk about, okay? You need to specify. Now, can we have one measure? Yes, we compute the area under curve, which is the AUC. And if the AUC for C1 or C2 is greater than the other, it said that C1 or C2 is better than the other. So if a classifier is perfect, its area under curve value is 1. If a classifier makes all random guesses, which is not like accurate, so this area is going to be less than even 0.5, okay, less than half. So these are examples. So here what we have, this is the ROC curve for one classifier, and it's having this shape, which is more near to the 100. So it converges quickly towards 100. So this is a good test. If it is like more near to that 50%, you see over here, this line, which is, I said, like the diagonal, it's the 50%. This one is more near there. It's far from the 1%. So this is a poor test. And these are other examples. So this is a perfect one. This is which having accuracy 100%, okay? This one is a 50% accuracy. And if it's a little bit more than 50%, maybe it's 56%. And this one, like, is almost near to the 100. Let's say it's a area under curve 90%, okay? 1% here, it's covering this whole zone. It's all colored. If you see here, this is the colored, it's like the percentage, okay? So the under curve here is covering 50%. The under curve here is covering the whole space, which is 100%. The under curve here, it's like 90%. Here is 65. Is this clear, please? Okay. So these are more examples I will keep for you. And I don't know if we have time. Oh, great, we have time. So we can probably go to the first algorithm, because if we talk now about like classification, we are introducing classification or metrics like accuracy, F1 score, area under curve, precision, recall, and so on. We need now to start studying these algorithms. So each of them, how it works, how given training data I'm going to test it, and at the end, our main objective is to study some algorithms and compare them in terms of these metrics, not only performance, okay? So we start with the KNN algorithm. And so in this case, KNN, K for an hyperparameter that you are going to set, okay? It could be 1, 2, 3, 4, or whatever. NN for nearest neighbor. So for this number of elements, I would say, I'm going to check the nearest neighbors. It's going to be K, like for, I can have one NN, it's for the one single nearest neighbor. 2 NN, I'm going to check among the neighbors, the most near, like 2 neighbors, 3 NN, and so on. I'm going to illustrate this one with one example, but before understanding the concept or mechanism, how this algorithm works, we need to take like a real case scenario. How it works. In the real world, imagine having florist. He wants to guess the purchase of of a customer X compared to his purchase N-1. So for each customer who's coming to buy a flower, probably this customer is having a record of purchase. So what we need to do is to guess or predict what he's going to buy this time, taking into consideration what he bought last time. So let's suppose last time he's buying a purple flower. So among this set of flowers, which one is going to pick this time?
Well, that's a tough one. You could compare prices, you could compare styles, you could compare, it's sort of the only two I can think of right now, but is that an example of the kinds of Ks that you can put in there is things like color and price? Or not?
So what we have now, like we have the information that previously he bought this one. So all you need to look is this one. You can guess. So you think he will buy this one?
No.
The green one? So which is your main feature?
The color and
The color. So you expect it to be
purple.
purple. How many purple flowers here we have?
3.
3. So, yep. So it's something like this. It's like somehow, now we start feeling the KNN. Now let's apply it. So, what we have? Which flower is a customer most likely to purchase based on similarity to previous purchases? So here, our factor is the similarity. It's not the cost. It's not the day, because if it's a Valentine Day, it's going to be red, absolutely. There is no question. So previously he's buying this one. I'm only going to be based on this one, which is mainly the purple one. So I'm going to check, like we said, it was intuitive. So we said it's like one of the purple, like this one, for example, or it could be another one or another one. So how we are thinking, if we are based on color and seeing the whole given data as like given the color and previous features. So we need to first think to check features, which is the properties of the data used for prediction. One of the features is the color, okay? We need to check the label. Maybe these flowers have some names, and I'm not a specialist, but there must be a name in general. If it's the same color, it's the same name, probably something like this. So the name here, it's the label. So the target value for a single data point. And we need the algorithm or the method for measuring the similarity. And in this case, it's going to perform classification. And here we are going to see the KNN. So let me ask you one question. Now, what is the difference now between if I give you this flower and I ask you to perform clustering, or I give you this flower and I ask you to perform classification?
Clustering is unsupervised and classification is supervised.
Okay. This is the most important answer. The second answer is The clustering, it's like when I was putting all the male in the start, female after, for example, or the opposite, which means I am collecting flower, grouping them based on a common feature, like which will lead me to put like the red flowers together, the yellow flowers together, and the green or other colors together, knowing that I don't have any information about the class. So in this case, we have the information about the class, which is the label, and this is why we are in the context of a classification algorithm. Is it clear the difference between clustering and classification? Online.
Yeah, that's
Okay.
clear, but I'm still
Yeah.
stuck on why you chose the color feature, and if you can choose a different feature for this situation, such that your clustering would be based on the price or whatever. So I'm just curious if it has to be something visual or if it's just what we're picking for this certain
No.
example.
We are just picking for this example. Otherwise, the features, we have a whole feature vector. For example, given a flower, you have information for the attributes we call, which are color, for example, price, I don't know if fresh or not, if for sale or not. So this is a whole vector. But we need to pick features here visually. The very clear feature is whether shape. This is why we are thinking of this one in the first level, which is exactly similar. Okay, it has the same shape, the same color. Otherwise, we only have this for now. But in general, we have a whole feature vector. Okay, but when we are using classification using KNN, now this is what we are going to see. It's like we focus on nearest neighbor. The nearest one is the one which is 100% similar, which is this one in this case. Next, we keep finding or fetching other elements which are very near, given for sure the feature vector, which is, if not shape, then let me think of color. I will give you an example. So in this, before giving the example, let's go through the process. So it's a two-step process. The first one is to construct the model from the training data, because in this case, the model is going to be trained. And next, the second step is to use the model to test the accuracy of the model test set and use it in the classification of future data if I'm talking about a new data. So the principle is very simple of KNN. So the K nearest neighbors algorithm is a supervised learning algorithm. So as Zoya was mentioning, it's supervised data. This is why we're talking about classification. If I don't have the class or label, don't talk on it. We talk about clustering. Now, so this is why we have the labeled data. Then from a set A of labeled data, it will be possible to classify or determine the label of a new data. And this is what we are going to do. It is also possible to use the K nearest neighbors algorithm for the regression. We seek to determine a value instead of a class, and this I was introducing at the start. Okay, so this algorithm is simple, but a very powerful classification algorithm. Classifies based on similarity measure. And when we talk about similarity, like you said, it depends on the feature. Similarity based on color, similarity based on numerical values, maybe the height or weight or price or I don't know what. So it's a non-parametric model, but it is known as lazy learning. Why is lazy learning? Because it does not learn until the test example is given. Whenever we have a new data to classify, we find its K nearest neighbors from the training data, which means this set of data which is given to you, this is the training data, and the K nearest neighbor is found given the training data. Okay, so this is what we have. Now we have this data in which there are two classes. The first one is survived, and the second one did not survive, for example. And I have on x-axis is the number of malignant nodes, and on the y-axis is the age, for example. And if the number of malignant nodes increases and the age increases, like mainly they are not surviving. If the number of malignant nodes is minimal and like the age varies, like let's say, and like for half of the number of malignants or whatever the age, it is survived. So if now what will happen? Imagine the scenario that we have a new sample and we want to predict to which class this new data point or sample belongs. So this one, do you think it is like survival or not survival?
Depends on K.
Yeah.
Yeah. So how we do this? We start K is equal to 1, which means I am going to check the nearest neighbor. In this case, it's based on distance. The most near one is the orange one. Okay, so here, this like diamond is expected to be class 1 orange. Okay, now I'm going to increase or increment the neighbor count. So K is going to take the value 2, which is going to take me. I'm going to consider the 2 nearest neighbors. The 2, which means the previous one, this is the most near, and the second most near one, which is this one. So based on this one and this one, I'm going to predict. Next, I'm going to increase the value of K, which is going to be 3. So my decision is going to be based on this one, and this one, the 3 most near points to this new point. So the K nearest neighbor has a very simple principle, which is to count like the distance and consider the K nearest neighbors, as the name is mentioned. Okay, as simple as this. So how it works, the algorithm is a 4-step algorithm. It takes input, a set of data D. What it does, it computes or it defines first distance function D. The distance function could be whether Euclidean distance or Manhattan, for example. So you define your distance function, and then you decide your KNN, how many neighbors you are going to consider. So this integer K you need to fix, and next a new observation X output. So here you predict the output variable Y of X, and this is how it works. The algorithm now, it begin and end. In the middle, we have for each new input X, calculate all the distances for this observation X with the other observations of the set of data D. Retain the K observation of the data set D close to X using the distance calculation function D. Take the K nearest neighbors as per the calculated Euclidean distance, for example. Among these K neighbors, count the number of the data points in each category and assign the new data points to that category for which the number of the neighbors is maximum, and algorithm. So in this case, this point is considered as
Survive.
yeah. So it is the blue because there are 3 blue points, 1 orange. So the majority is the one deciding to which it's more near. Okay, this is how it works. Okay. The problem and the biggest problem now, how to choose K. If we consider this case, for example, imagine here, K is equal to 2. What you have, it's near to the orange one and to the blue. So somehow, even that it's more near to the orange, we absolutely assign that to the orange one if K is equal to 1. We are sure. But if we are adding a new K, this is making us confused. So there is no clear decision. Okay, so one of the biggest problems, it's the choice of K. So if K is too small, it is sensitive to noise points. So you can imagine even this orange one we were discussing now, this is a noise because this region, it's all belongs, let's say, to the blue class. And even this one is the most near, it's an outlier. So we cannot decide that this is, for example, it's not survival at the time that the not survival, which is near to this point, is an outlier. Okay, so this is why we must not trust when k is small. You see here we are increasing the number of k is 3, so we are more sure that most of the neighbors are survival, and we are changing the decision. Okay.
Out of
Is that-
curiosity, can we just hit that whole half with a GMM and get rid of the outliers before we do this? Is that a form
Yes,
of data
sure.
cleaning?
Sure. The thing of the problem that outliers, even in GMM, we see that.
Mhm.
That outliers is a problem that's always there.
Okay.
Okay, GMM is an option, but for me, I don't see it solving the problem of outliers for now. I can take you to the example of where we see in GMM here. So I was drawing on, okay. You see here it's cluster 3. I said that you find here some points from cluster 2. So sometimes having the points, it's not really reflecting like this, for example. This is an outlier. So outlier problem is in general always there, but how to solve this problem? We can solve it using KNN itself, just by increasing the k. So if I will see more neighbors, so I will confirm this is just an exception. It's not the general case. By increasing k, maybe I can solve this problem. So we go back to our, did I answer your question, Jeremy?
Yeah, I guess I was expecting to
Right.
like get rid of it with a GMM so that we wouldn't have to worry about changing our K or whatever, but maybe that's just not how it works.
Okay. So if k is too small, is sensitive to noise points. We're discussing these points. Now, larger k works well, but too large k may include majority points from other classes. Okay? So, which makes sense. If you are considering larger k in this example, so you are going to consider like elements from the other classes. In this case, for fixing k, I can let you ChatGPT it, but there is one very famous rule, which is the rule of thumb. The rule of thumb says that the k must not exceed the SQRT of n, which is where n is the number of examples. So at some point, you need not to exceed that thing. So you use the SQRT function of that number n. Like every algorithm, like KNN has its strengths and points, like advantages and disadvantages. So for the advantage, there is no training period. KNN is called lazy learner or instance-based learning. It does not learn anything in the training period. It does not derive any discriminative function from the training data. Means there is no general model. It stores the training data set and learns from it only at the time of making the real-time prediction. So I need to have my sample here so that I would be able to compute the distance. Okay, so this makes the KNN algorithm much faster than other algorithms that require training, like linear regression or deep learning. I don't know. So since the KNN algorithm requires no training before making predictions, new data can be addressed seamlessly, which will not impact the accuracy of the algorithm, and that's great. So KNN is very easy to implement, and we will see that. So there are only 2 parameters required to implement KNN, like the value of k and the distance function, whether Euclidean or Manhattan or any other one. So now what we will say, so for implementing the KNN, like we've seen for k-means, there is just one line of code. You call the algorithm, you fix k, and that is it. The whole problem for whatever algorithm in general is the pre-processing step of data. It's to visualize data, it's to clean data. And this is the really hard task, okay? So I was discussing with one of the students in this class who is not here. but he maybe see the like videos later. We're discussing about the use of machine learning in the context of cybersecurity. At UM Flint, when I was taking a look on the course listing, there are classes for the cybersecurity where AI is there, where trustworthy AI is there, ML is there, and they apply the machine learning algorithm. So his question was, how can we apply machine learning in a cybersecurity context? Can you answer this question?
You can classify network traffic by certain parameters and then identify it as a threat or a legitimate request.
Yes, so this is the case. So when we talk about like domain of application or the field, so this is called the business, okay? So the business is the same as we can use these machine learning algorithms given images of skin cancer. I can use given records of data with like the example that Jeremy is mentioning with the cyber like security context. The thing is that for both cases, it needs from me, okay, the KNN algorithm is very simple. Everyone is understanding. Coding, I will be showing you next time, it's just one line. The whole thing is to understand the business. And when we talk about business understanding, this is a step. If you are working as a data scientist now, what you will do is it's not only that you are the expert of machine learning algorithm and things, you need to have some methodology. And one of the very famous methodologies is the CRISP-DM, for example. There are many. You can like even use ChatGPT to ask, as a data scientist, I have a project like related to cybersecurity, for example, and I'm going to use machine learning. Which methodology do I need to use? So maybe in data science class, you can like have like courses about the choice of this methodology. But the steps, like to sum up, are very logical as someone who is not expert in cybersecurity, for example. I am having data which is belonging to cybersecurity. You can imagine that I'm talking about any field, okay? Or medical data, or I need to understand the context. I will not be the expert of it, but I need to spend some time reading about it, even asking ChatGPT about it, understanding things. Now, once I understand the business, next I need to see my data, because when I see data and I'm not understanding the business, I won't understand data. If I have like an idea about the business and I'm done with the business understanding, let's say, I can like get help from experts in that field or internet or whatever resources. Next, I'm going to see my data so I am able to understand. Now your job will be like a data engineer. And when we talk about data engineer last time, when we were introducing machine learning, we said the first step is data. Like here we are manipulating simple data, reduced size data. Like this set of machine learning algorithms in general, most of the like disadvantages, it does not work well with large data sets. This is a very huge challenge, okay? So the data set size is a challenge. This is why when you talk about data engineering, the first step is to collect data. When you talk about collecting data, and I also liked at UM Flint, there is courses designed for data engineering, which are different from AI. I was teaching data engineering, and when I was applying to teach that, I thought it's AI. At the end, I was really learning with my students that it's a different context. We are not talking about data similar to this one. We are talking about huge data. We are talking about big data. We are talking about data lakes. We are talking about data warehouses. So you imagine you are doing kind of web scraping. So you are collecting data from everywhere. And you imagine the amount of data that you can deal with. So cannot import simply. You cannot, or imagine that you are working with real world data. It's another problem. So in this case, the ML project is the same. They can still use ML algorithms or deep learning, which is the model, which is the architecture. But this first stage really needs like years of specialization, expertise, to show that you are able like to connect data, to draw like the schema, how to model that data, to like after that, like next apply the ML model or AI model. So this is the first step. So KNN does not work well with large data sets, does not work well with high dimensions, needs feature scaling, and sensitive to noisy data, missing values, and outliers. Okay, so next time I'm going to share with you a notebook for the KNN. We'll go through this in the class. I would show you the first stage, which is a huge stage. You may focus with that with a machine learning class, and we'll show you how to call the KNN algorithm, which is just a simple instruction, like one line of code. Okay, so any questions for today? Online?
What's a good first step for our groups for the machine learning portion? Do we have to pick like a subject that we want to approach it at, or how are we going about that?
It's AI.
Okay,
The first step is what we are doing. The next step depends on your context, because in the AI class, you are seeing from basic to advanced concepts. So now you are familiar with the mathematics background behind this whole thing. Now you will see yourself where you can see yourself. You can see yourself as data engineer. You can see yourself as data scientist. You can see yourself as a researcher. You can see yourself like just ML developer. So here it depends on your position. You can see yourself as an architect. So architect is someone who don't care about all these things. I'm going to have a team, and in this team, I'm going to have, for example, the one specialized on this data collection and things. I'm going only to give you the overall architecture, how it's going to be. We are going to test and work in team. So no one could be, I'm going to say this, no one could be specialized on everything. Because if we have a department, we have a team, everyone is going to do something. But your job is to focus whether on data engineering task, where you will deal with, maybe you will take data, advanced database courses, you take data engineering class, maybe you will focus on the data science part, mathematics side, model side, machine learning classes. If you have the idea of your business, there is courses for AI with healthcare and other, they maybe teach you there what they don't teach in the classes of AI with cybersecurity. AI with healthcare can teach you. I remember I was attending one seminar, the way to upload MRI data is a completely complex task, because MRI data itself, to study, to understand, to upload itself needs work. It's completely different from the context of, like, for example, cybersecurity. And there is programs here where you study ML for cybersecurity. There is programs where you only study ML for general purpose. So it's up to you. It's up to your position. It's up where you see yourself, I think.
Maybe I wasn't clear. I meant for the groups for the project for this class. We have to make all those decisions before we move forward with our project in this class. I'm just trying to figure out.
It's a very simple question in this case. So in the class, I am just giving you an idea about the algorithm. You are going to apply in the particular case. You also need to go through your business, understanding the data sets are in general clean. If one of them is not clean, you may try. It depends. So for the project, it's a very simple task. You have data, MNIST data you're going to classify. You have cancer data you're going to classify.
Have you provided that data though? Because I only got the cars.txt.
I'm waiting for the groups for me
Gotcha. Okay.
to
I
be
just wanted to make
finalized.
sure.
But next week, I'm sure this group must be done. I'm going to add this as an assignment. I believe only this it will work. Assignments with deadline like Wednesday. So I make sure by Wednesday everyone is ready. So Wednesday I can provide you with data set and everything. Otherwise,
Gotcha.
until that time, if you have time, you can take a look on other algorithms. If you want to get extra points, you can interact with me during the lecture, during the class time. So for example, next time we will see the SVM. If you want to prepare a presentation, I say you or anyone means you can have presentation to improve your marks, to get extra points. And like this, at the same time, it's for your project, it's for your extra points, and it's for everyone. So I'm always open. Anyone who wants to send me email to interact with the future like sections, I am not against this. Okay.
Okay.
Other questions? Online? I think no. Okay, so see you. Thank you.